Dr. Rico here. This is an introduction to my mini course, Robotic Planning and Kinematics. The syllabus link and notes are in the description. Alright, so section 1.1, Problem Setup and Modeling Assumptions. Motion planning is an important and common problem in robotics. In its simplest form, the motion planning problem is how to move a robot from a start location to a goal location, avoiding obstacles. This problem is sometimes referred to as the move from A to B or the piano mover's problem. How do you move a complex object like a piano in an environment with lots of obstacles, like a house? In this first chapter, we consider a sensor-based planning problem for a point moving in the plane R2. In other words, we assume the robot has a sensor and, based on the sensor measurements, it plans its motion from start to goal. To properly describe the motion planning problem, we need to specify what capacities does the robot have? What information does the robot have? In this chapter, we make the following assumptions on the robot and its environment. As illustrated in figure 1.1, right here, we are given a workspace W, this whole box here, that is a subset of R2 or R3. R2 in this case, right? Just the plane, often, and in this case, just a rectangle. Also, some obstacles. Obstacle 1 or O1, O2, up to ON, N obstacles. Here is an obstacle O1, here is an obstacle O2. A start point, P start, which is here, and a goal point, P goal, over here. And a robot described by a moving point. Okay, so that's going to start at this point, go to this point, and it will be represented by a point in between. So in this case, the robot has zero size or zero volume in this space. Later we'll consider what happens when you have a volume to your robot. And of course it adds complexity. We define the free workspace, W free, equal to W, the whole workspace, minus the union of the objects, 1 through N. Okay, so this is set minus. We take the set of space minus the set of space that is contained in the objects. So this is the set of points W that are outside all obstacles. Recall the definition of the set A minus B is, in set builder notation, all the elements of A such that A is not an element of B. That is, all points in A that are not in B. That's the set minus operation. Robot assumptions. We also make some assumptions on the capabilities and knowledge of the robot. We assume the robot knows the direction towards the goal, knows the straight line distance between itself and the goal, does not know anything about the obstacles, their number, location, shape, etc., has a contact sensor that allows it to locally detect obstacles, can move either in a straight line towards the goal or can follow an obstacle boundary, possibly by using its contact sensor, and has limited memory in which it can store distances and angles. We discuss in more detail later what these robot capabilities imply in terms of robot sensors and knowledge. Our task is to plan the robot motion from the start point to the goal point. This plan is not a pre-computed sequence of steps to be executed, but rather a policy to deal with the possible obstacles that the robot may encounter along the way. Knowing this, which type of control architecture are we using here? General robot control architecture. Is it deliberative? Is it reactive? Is it hybrid? Think about it. Environment assumptions. Finally, we make some assumptions on the workspace and obstacles. The workspace is bounded. There are only a finite number of obstacles. The start and goal points are in the free workspace. They're not inside an obstacle, for instance. And any straight line drawn in the environment crosses the boundary of each obstacle only a finite number of times. This assumption is easily satisfied for normal objects, and we will use it later on to establish the correctness of our algorithms. We don't have any obstacles that are defined by fractal boundaries, for instance. In the next sections, we see 3 different algorithms for planning the robot motion from start to goal, called the bug 0, bug 1, and bug 2 algorithms. We're zero indexing these algorithms. Each algorithm has slightly different requirements on the robot's capabilities and knowledge. As a result, we will also see that they have different performance in finding paths from start to goal. All right, that's all I've got for this section. See you in a sec.